Welcome to the program. I'm Jeff Schechtman. The great screenwriter William Goldman once said of Hollywood that nobody knows anything. The physicist Richard Feynman once said that no one understands quantum mechanics. And yet, random as knowledge sometimes might be, it's safe to say that the entire technological infrastructure of modern society, all of Silicon Valley for that matter, is built on top of the reliable functioning of quantum mechanics. Quantum mechanics has been around since 1927, and yet we still don't fully understand how it works. It's a little like being able to tell time and use the value of the information of time, and yet not having any understanding of how a watch works. We're going to talk about exactly this today with my guest, Sean Carroll. Sean Carroll is a theoretical physicist at Caltech. He is host of the Mindscape podcast and the author of the previous books From Eternity to Here, The Particle at the End of the Universe, and The Big Picture. He's been awarded prizes and fellowships by the National Science Foundation, NASA, the American Institute of Physics, and the Royal Society of London. It is my pleasure to welcome Sean Carroll back to this program to talk about his newest work, Something Deeply Hidden, Quantum Worlds and the Emergence of Space-Time. Sean Carroll, thanks so much for joining us.
Hey, thanks for having me.
Well, it's great to have you here. Talk first about why quantum mechanics is important. Not so much important for us to understand, we'll get to that, but why it's important for the functioning of the world that we live in the 21st century.
You know, my favorite example is actually the fact that atoms wouldn't be stable if it weren't for quantum mechanics. You know, you have this picture in your mind of an atom with a little nucleus and there's electrons orbiting around it. But those electrons, if it weren't for quantum mechanics, would simply fall right into the nucleus in a tiny fraction of a second. So just the fact that your tables and chairs are stable and don't collapse into nothingness right away is ultimately due to quantum mechanics. Of course, we also needed to understand transistors and lasers and things like that, as well as things like why the sun shines.
Why has it been so difficult to really get a simple understanding of quantum mechanics? As you write about, and I mentioned in the introduction, it's been around essentially since 1927, but it's been difficult to explain to people.
Yeah, I think that's absolutely right. And it's not just difficult to explain to people, it's difficult for physicists themselves to really understand what's going on. And the main reason is because quantum mechanics is different than any other theory of physics ever invented, because it seems, on the face of it, to require different rules for what quantum objects do when you're not looking at them versus when you are looking at them. That's just bizarre to us, and we haven't quite come to grips with what that really means.
Expand on that a little bit as it relates to sort of the fundamental principles of kind of Newtonian physics, this idea of position and velocity.
Yeah, if you were living in a Newtonian world, if Isaac Newton had been correct, then there's this wonderful feature that if you know the position and velocity of a system, like the Earth orbiting the sun, you can predict what that system is going to do arbitrarily far in the future, and astronomers actually do this. But quantum mechanics says the state of a system, the information you need, is a different kind of thing. There's not really any such thing as the position or momentum. What there is this spread out cloud of probability that we call the wave function. And what we can do is use that to predict the probability that we'll see something if we look at the system, but you can't with absolute certainty say what the result of that measurement is going to be.
In terms of trying to understand that measurement, explain how that goes to the heart of this difference between something being a wave versus a particle.
I mean, roughly speaking, it's a simple distinction. When you're not looking at things, they behave like waves, and when you do look at them, they behave like particles. The mystery is, what do you mean look at something? Like, how in the world is that supposed to be a part of a fundamental theory of nature? That just seems to make no sense to us.
Mm-hmm. And explain how it makes sense, how the evolution of the idea in quantum mechanics.
Well, it took a while. I mean, that's the interesting thing. We think of general relativity, Einstein's wonderful theory of space-time, as one of the crowning intellectual achievements of physics. But that was basically one guy, Einstein, thinking about it for 10 years. whereas quantum mechanics took dozens of people more than 2 decades to figure out. So it really was something we crept up on, and it started by people like Einstein saying things we thought of as waves, like light, have particle-like properties. And then other people like Niels Bohr saying things we think of as particles, like electrons, have wave-like properties. And we finally settled on this weird, uncomfortable compromise where things were waves until you look at them very carefully and then they look like particles.
Mm-hmm. And then there seemed to be those people that said it didn't matter as long as we sort of understood how they worked.
Yeah, this was a major thing where there was a debate, especially between Einstein and Bohr, Niels Bohr, one of the founders of quantum mechanics, about whether or not this ramshackle set of rules we put together in the 1920s was good enough. And Bohr and his colleagues in Copenhagen argued, we've got it more or less figured out, whereas Einstein and others said, no, it's not yet finished. We're not complete. We need to dig a little bit more deeply. And Bohr and his friends won the public relations battle. So physicists worldwide took the attitude that we knew enough about quantum mechanics. We should get on with our jobs of putting it to work rather than worrying about what it really says.
And the effort to really measure it, to see it, to understand that there was this difference between what we understood versus what we would see, and how that debate evolved.
Yeah, this is a fundamental mystery of quantum mechanics, that we have a way of talking about things in terms of these clouds, these wave functions. We can use that like almost as a black box to predict what we will see. But not only are we a little bit vague about what it means to see or to measure or to observe, if you say, what is the wave function really? Like, is that reality that we're talking about? Or is it part of reality? Or is it just a way of us expressing our ignorance about reality? And even these very simple fundamental questions, scientists don't agree on. And I think that it's really holding us back as we try to push forward and try to understand the fundamental nature of the universe better.
And when we understand it, talk about how it relates to general relativity and how that gives us the starting point into some of this.
Well, general relativity, like I said, it's Einstein's theory of space-time and gravity, a huge intellectual achievement on the one hand. On the other hand, it's the one part of physics that doesn't seem to play well with quantum mechanics. Quantum mechanics is, if anything, more fundamental than general relativity, but with every other part of nature, whether it's matter particles like electrons and quarks, or forces like the nuclear forces of electromagnetism, we can start with a well-defined classical theory and convert it into a quantum mechanical theory. With general relativity, we seem to fail at doing that. We can't quite come up with the quantum mechanical theory that reproduces the successes of general relativity when it comes to gravity. So people like me are saying it might be that we're hamstrung by trying to start with the classical theory and quantize it. Maybe we should start with the quantum theory from the start and find classical space-time within it.
And how does this idea of this many-world theory, this many-world point of view of quantum mechanics, how does that relate to what you're talking about?
Well, many worlds is a wonderful label because it's evocative and colorful and poetic, right? But it doesn't really capture what the theory is about. Hugh Everett, the graduate student who in the 1950s started pioneering the many worlds approach, he never called it that. His idea was simply, look, the universe, including observers or apparatuses or whatever, everything is quantum mechanical. It's fundamentally quantum mechanical from the beginning to the end. And there's no special extra set of rules for measurements or observations. There's just the ordinary rules about how wave functions evolve. And what he showed, what he argued, was that if that's true, individual people in the universe would experience the world as if it were random and stochastic, and there was a probability of different things happening. But what's really happening is one universe is branching into many. And in all the different universes, there are different observers who got different measurement results. That's what is predicted by the fundamental equation of quantum mechanics.
And has there ever been experimentation or anything that would cause us to question some of the fundamentals of quantum mechanics?
Not really. I mean, quantum mechanics is something that, as I said, we don't quite completely understand. So there are actually different versions of quantum mechanics. There are different theories which all, in up to current experimental limits, produce the same experimental predictions. So we don't know which formulation, or maybe we haven't even thought of the right one, which will eventually get it right. But in terms of the basic framework of quantum mechanics, everything we've ever done in all of physics is completely 100% compatible with that.
And what are the limits of the research at this point? What do we still need to be able to do? What would ideally we be like to be able to do to further give us insight into this?
I think that, we're at a point right now where there's a bunch of experiments going on, but none of them has the character that they're guaranteed to teach us anything surprising. Like, one of the reasons why fundamental physics has slowed down a little bit is just because our theories are too good. The experimentalists are great at pushing their apparatuses into regimes we've never seen before, but every time we do that in the last couple decades, we've seen kind of what we expected, and that makes it really hard to make progress. So I think what we need to do is sort of take a step back and think about the fundamentals again, think about the foundations, start trying to answer some of these difficult questions about what quantum mechanics really means.
Expand on that a little bit. What are some of those questions that we need to be asking? How far back do we need to go?
Well, if we don't know what exactly happens when you make a quantum measurement, that's one big problem. But the other problem is we don't know what the world is, okay? Part of what you would think physics is supposed to do is illuminate the fundamental nature of reality. So we don't know whether wave functions are exact copies of the world. Is it a perfect representation of what's going on? Are there other extra hidden quantities other than the wave function that are there in addition to it? Or does the wave function have nothing to do with reality? Is it just a way of making predictions and reality is something different entirely? If we don't know the answers to those questions, how in the world can we hope to talk about space-time and quantum gravity and the origin of the universe? So I think thinking deeply about these foundational questions about what the world really is the obvious next step.
And from an experimental perspective, what do we need to be able to do?
Well, it's a fishing expedition right now. Like I said, there's no experiment that we're doing that is guaranteed to bring us something really surprising. But there's plenty of experiments that could bring us something surprising if we're lucky. So we smash particles together at really, really high energies. We look at the leftover radiation from the Big Bang. We look at gravitational waves from black holes. And as you know, we recently took a picture of a black hole up close and personal. So if we can improve all of those things, we're bound to hit something that we didn't expect, and that's where we'll really learn something.
So it really is, it's kind of a hit or miss exercise in some respects.
It is. It's a weird situation to be in because on the one hand, the theories we have right now fit the data. They're not being contradicted by any experiments we've ever done. But on the other hand, we know these theories aren't right. We know they're not the final answer because they're kind of internally inconsistent. Gravity is described by general relativity. Particle physics is described by quantum mechanics. But general relativity and quantum mechanics don't play well together. So even though they both individually fit the data, they can't both be right. We need to do better.
And do we need to go back and rethink the whole idea of general relativity? Is that part of this exercise?
I think that general relativity will continue to be useful in the regime where it's useful. So general relativity does a great job at explaining what happens when the universe is expanding or in the solar system and so forth, but it's not the final answer. So I think that your question is a good one. Rather than starting with general relativity and trying to force it into a quantum mechanical box, we should think quantum from the start and ask how in the world could the universe as described by general relativity, with its curved space-time and expanding universe and stuff like that, how can that emerge out of quantum mechanics? That's why emergence of space-time is part of the subtitle of my book.
Within the community of physicists today, talk about where the debates are, where the different points of view break down.
Oh, there's so many. I mean, that's what scientists are so good at doing, is debating with each other. That's what we love to do. In quantum mechanics, there's sort of mini debates about what is the best version of quantum mechanics. Is it many worlds, or is it hidden variables, or is it something different? There's another debate about, whether we should even worry about the foundations of quantum mechanics. But this is kind of a silent debate. People have their opinions, but they don't, no one has a conference to argue over whether or not we should take the foundations of quantum mechanics seriously. If you don't take them seriously, you just ignore it, right? So that's one set of debates. Then there's a million other debates. What is the dark matter? What happened at the Big Bang? What happens inside black holes? There's no end of controversies in modern physics.
And then, of course, people that come along and want to try and find the spiritual element in all of this.
Yeah, and I think that the spiritual element is not something extra. I think that the universe is the universe, and it's a physical universe. It's a universe that obeys the laws of nature, and things like purpose and meaning in life are things that we create out of the universe. You don't need to tack them on.
Talk about where the work, the concentration of work is being done into some of these questions. You're doing some of it at Caltech. Talk a little bit about what that universe of physicists looks like.
Yeah, I think that all of the major universities of the world have people who are physicists. Physics is definitely one of the foundational disciplines within academia. But it's very interesting how what problems are considered interesting and worth thinking about change from place to place. The idea of a multiverse, for example, that cosmologists like to talk about, most people who take the multiverse seriously in the United States are on the West Coast. In fact, most of them are in California. The idea of a multiverse is not that interesting to people on the East Coast. They like to do more mathematically well-defined problems. But there's a huge number of places where very exciting work is being done. Berkeley, Stanford, Harvard, MIT, Princeton, all over the place. There's brilliant physicists trying to figure this stuff out.
One of the things you've talked about is how to look at this as kind of a closed system and what that means.
Yeah, closed system is one that you can describe all by itself. If you pick up a baseball and throw it, the baseball is not a closed system because you're influencing it. You picked it up and threw it. If you take a bottle of soda and you put it in the refrigerator, it cools down because it's not a closed system. It's being influenced by the refrigerator. But a closed system, you don't need to worry about external influences on it, and that makes things a lot simpler. And we think that the universe is a closed system. We don't think there's anything outside the universe that's pushing it around.
And are there those that argue differently, that there are outside forces, that in fact that there are some other reasons, or maybe that we have to just live with this difference between quantum mechanics and general relativity?
Sure. The wonderful thing about physics is if you ever ask, are there people who argue, there always are people who argue that. There's always someone who has almost any opinion. And, that's the way it should be. There's certain avenues, there's certain ways of thinking that seem to me or to other people to be more promising. But it's important to keep various different prospects alive at any one time, to keep all the options open until we really are sure what's going on.
And talk about your views on this and whether you think that there ultimately will be some explanation as to this inconsistency between these two theories.
Yeah, sometimes people wonder whether or not the difficulties in understanding this or that theory reflect the fundamental inability of the human mind to come to grips with concepts such as these. But I do not have any sympathy for that point of view. I'm just the opposite. 100 years ago, we didn't understand what a wave function was. We had never heard of those things. And 100 years is a very short period of time, cosmically speaking. So it's extraordinary impatience to say, well, if we haven't understood it in 100 years, we never will. I think that's a crazy way of talking. I think we definitely will understand these things if we just keep trying.
Sean Carroll, the book is Something Deeply Hidden, quantum worlds, and the emergence of space-time. Sean, it's always a pleasure. I thank you so much for spending time with us.
My pleasure. Thanks for having me on.
Thank you.